So here we are in the sort of last big quantitative lecture for the course, which is to see on a circuit level how this new circuit element of the inductor fits into our understanding of how we approach circuits with Kirchhoff's laws and differential equations and things like that. Now, what I'm showing you here is nothing explicitly to do with inductors, but it is a means of sort of completing this water analogy that we've been using throughout the course as an analogy for what goes on inside a circuit. And we can think of many of these circuit properties as having the analogy of water flowing through pipes. And the role of the inductor is to limit changes to a circuit, limit changes to current in the circuit. So if we think of current in these water pipe analogies as the flow of water, something about the inductor should be how it limits, the analogy should be something about how it limits the changes to the flow of water. And effectively what we're looking at in that analogy is just the momentum of the water itself. That sort of plays the role of inductance. That imagine one of these setups here. If you've ever seen these before, these are magnetic stirrers used in chemistry to stir a solution sort of automatically. When you turn it on, it starts spinning a magnet, and that doesn't immediately get all of the water moving, of course. It takes time for that water to sort of get up to speed because that water has momentum. It wants to stay where it is, and it takes the force of that magnetic stir sort of pushing it around before it builds up speed. That's sort of the role of the inductor here, is that when you turn the battery on, you don't immediately get current moving around. It takes time to build up as it passes through the inductor. And then you could imagine in reverse. If I turned off the magnetic stir, the water doesn't just immediately stop, nor does current immediately turn off in an LR circuit, because it has that quote-unquote momentum that leaves it sort of to come to rest slowly over time. It's an analogy. It's not perfect, but it does give a nice sort of conceptual motivation for what's going to happen today. But the real story is the more rigorous approach. We'll talk about it a little bit qualitatively to remind ourselves from the last video, but then we'll jump into sort of doing the same things we did for the RC circuit of talking about what it looks like at t equals 0 and t equals infinity, and then we'll go to a full analysis using some of our old methods from the RC circuit as well, including finding what the time constant is. So let's remind ourselves, last time we saw that inductors, their big role is to limit the rate of change of current in a circuit. So if we were to set up a circuit like this, we know that we can't just immediately get up to max current. We have to build it up slowly due to the presence of the inductor. But of course the question is, how long does that take? What would affect how long it takes? Presumably the values for the inductance and resistance might have an effect. Maybe the voltage of the battery would have an effect. And we'd like to figure out exactly what the rate for doing so is and mathematically what that looks like. But we're going to start with just understanding the limits. Let's say here's all our actual values for the battery, inductance, and resistance. And let's do our t equals 0 and t equals infinity analysis here, purely just based on our conceptual understanding of the inductor's role in a circuit. If this circuit sort of began disconnected, right at t equals 0 after closing that switch, what should be the current in the circuit purely conceptually? Pause here and see what you think. All right, I hope you got 0 amps. Because you can't just go from no current, which is of course what's going to happen in a disconnect here, to closing the circuit and immediately getting current. The inductor says you have to build it up slowly, so right after it's closed, you can't have built up anything quite yet. You are sort of immediately starting to build things up, but right at that second, you still have not been able to make an instantaneous jump, because that would have meant an instantaneous jump in magnetic field, which Faraday's law would completely disallow. So given that, what's the voltage on the inductor? Pause here and see what you think. All right, I hope you got 20 volts. That is purely from the loop rule. If there is no current in the circuit, there's no voltage on the resistor, which means that the inductor is getting everything. So that's our t equals 0 behavior. Let's see what we think after t equals infinity. After the circuit has had a long time to sort of build up and do its things, what do we think here? Pause to see what you think for the voltage on the inductor. All right, welcome back. I hope you said 0 volts. What's going on here? Well, we know that after t equals infinity, it builds up to this constant current. And once the current is constant, we know that voltage on the inductor depends on the rate of change of current. So if it's constant, its derivative is 0. You can think of that more sort of physically as once the current is constant, the magnetic fields produced by those currents are also constant. So if the fields are constant, Faraday's law says there's no need to induce any voltage. You only get voltage when you try to change the current. And if there's no voltage on the inductor, what must be the current in the circuit? See what you think. All right, I hope you got 2.5 amps. That purely comes again from the loop rule. If there's no voltage on the inductor, that means that there are 20 volts on the resistor, and then one application of Ohm's law, V equals IR, will give you the current of 2.5 amps. So you can see that we are still, just with our conceptual understanding of the inductor and its role that it plays in the circuit, we can still understand the limits without necessarily needing to understand what's in between. And those limits kind of look like, for t equals 0, the inductor says you absolutely cannot pass current through me because you can't go from no current to some current instantaneously because that would mean an infinite voltage in Faraday's law. And then after a long time, after the current has equilibrated, now there's constant fields through it, so there's no need for any voltage, and it's like a blank wire that you can pass through with no problem because you're not changing the fields through it. But there's a little more to the story than that. It can't just be a break, because see what you think purely conceptually about this question, where I have connected my LR circuit up to a battery and left it to run for a while. So it has reached its equilibrium, and we've built up our sort of steady state current here. And then I'm going to flick the switch over to 2, removing the battery from the circuit, and just putting the inductor and the resistor in their own loop. What's going to happen the moment after the switch is moved to this new position? What's the current in the circuit look like right when I close the switch? Pause here and see what you think. Well, again, from our idea of not being able to change current instantaneously, it should be whatever the current was right before I closed the switch, because any other change would have meant you changed current immediately, which Faraday's law would never allow because you would have changed the fields immediately. And before we closed the switch, we had built up to a steady state current where there was, again, no voltage on the inductor, 12 volts on the 4 ohm resistors, that means 3 amps. What would happen now a long time after the switch were moved over to this new position? See what you think now. All right, I hope you said now in this new situation after a long time, there would be no current. This is conceptually the situation we looked at the end of the last video, where current is going to sort of leak away and go down to 0, but the inductor just limits how quickly that will happen. But we do still wind up getting to 0 volts, 0 current in the circuit regardless. That current does leak away, but it happens slowly. Okay, so we've seen that maybe our idea of treating the inductor like a brake is not quite correct. What's maybe a little better is to treat it like this current-preserving object that will always force the current to stay exactly where it was right before any switches were closed. But the t equals infinity behavior is still good. It still looks like a short after a long time. So now that we've seen what the limits look like, it's time to understand what happens in between. What happens in between t equals 0 and t equals infinity? How long does it take to build up to the equilibrium current? Well, we know that we're going to analyze this with the loop rule. That's how we analyze everything. And if I start with a loop rule for this circuit of gaining voltage on the battery, losing it over the resistor and the inductor, and plugging in the definitions for voltage on each, Ohm's law for the resistor, L times the time derivative of current for the inductor, I wind up with a relationship here, which is, again, a differential equation. It has current and its derivative in the same equation. I'm afraid now. Does that mean I have to go back to the drawing board? Am I scared of differential equations? Well, of course I am, but for the sake of this course, it actually looks very similar. I'm kind of getting some flashbacks here. Remember, this was the method we used for the RC circuit. It said anytime you can create a differential equation which looks like this, you'll always be able to get to some kind of function here, something exponential. And indeed, that's what I have. I have a constant plus something times my variable, here to r times I, and then plus another something times the first derivative of my variable being current here. So we are actually back in a scenario where we get to use the methods of the RC circuit. And we've already done the t equals 0 and t equals infinity. So we already understand that we can find A and B for any LR circuit, and we know that it's going to be exponential. The only thing we don't know quite how to do is figure out what's the time constant. So we understand that the buildup or the leakage of current is exponential, but exactly how fast does it happen? Well, our old method said that that's determined by the loop rule, and this was our loop rule. And let me sort of draw the analogy. This was the loop rule back from the RC circuit that gave us a time constant of r times c. And here you can sort of see, we can draw down all the analogies that I maybe can plug in r for 1 over c, or maybe 1 over r, and then L takes the place of R. If I sort of put that analogy together, I get actually the right answer. Now, of course, you would get this by doing the full differential equations analysis, but I've just sort of skipped and connected the dots here and said, this does actually work to sort of draw analogies and find a time constant of L over R. Conceptually, does this make sense? Bigger inductance says any change of current in the circuit is going to take longer. It's harder to change current in the circuit. So definitely makes sense that bigger inductance is going to increase the time constant, sort of slowing the behavior down. Maybe more interesting is the fact that increasing the resistance actually decreases the time constant. What's going on there essentially is that you have less distance to go. That when you increase the resistance, you don't have to go as far to build up to your max current, because increased resistance lowers what your maximum current is going to be, so therefore it feels like it's easier to get there in some sense. That's my loose conceptual argument for how you'd find, or why you would motivate increasing the resistance, decreasing the time constant. And then that's it. Given everything that we've done before, this should just be an application of the things we already understand. Time constant given to us by the loop rule is now L over R for the LR circuit. Our t equals 0 and t equals infinity behaviors are purely just with our generic circuit techniques that we have practiced earlier in this video, and we should be able to put it all together. This is a bit of a tough question, sort of follows from some of the RC circuit workshop material, but definitely spend some time with it. Give it a good long pause and see if you can get the right answer here. All right, welcome back. If you're able to get to the end, I hope you found C of 11.2 amps as your final answer. Well, let's see how we got to this. We'd like to derive the current over time through the battery. And we know that it's going to follow now some exponential behavior because we wound up with the same kind of loop rules we did back in the RC case. And to find A and B, we should find what's the current through the battery at t equals 0 and at t equals infinity. And how do I find those? Well, I can use my limiting behaviors. Say at t equals 0, the inductor does whatever it has to keep the current exactly what it was before. And before the switch was closed, we had no current. So right at t equals 0, that inductor is completely shutting down that middle branch. It says absolutely no current can go through that middle branch at t equals 0 because no current was going through it the moment before. So this circuit really only looks like it has the top branch here of 4 ohms and 25 volts, which, thanks to Ohm's law, is going to give us I0 being 25 over 4 of 6.25 amps. Wonderful. then at t equals infinity, we know the inductor just behaves like a short. It says it's having no effect. We've equilibrated, and we have now sort of almost entirely removed the inductor from the behavior. And we can just combine these two resistors in parallel. I go 1 over 2 plus 1 over 4, and I invert that. I get 4/3 ohms for 25 volts. Quick application of Ohm's law there. 25 over our resistance gives us 18.75 amps as the infinity resistance. Okay, now sort of returning to our analysis of trying to fill in our A, B, and tau, we know that B is equal to I infinity, which is 18.75, and A is equal to I0 minus I infinity, which is I0 is 6.25 minus 18.75, which is, throwing that into my calculator, minus 12.5. So putting this together with what we have so far, we have that the current in the battery over time is minus 12.5 e to the minus t over tau plus 18.75. All that's left to do here is find tau and then solve. Well, we know tau just comes from the loop rule, and only the resistance within that loop should contribute. So tau should just be 16 over 2. Because the 2 is the only resistor in that loop. So in total, our full expression of how the current in the battery evolves over time has been fully specified. And then we just ask, the question was saying, what's the current after 4 seconds? So then we just take our exact function, we plug in 4 for time here, and all of that can go directly into our calculator, giving us 11.2. Excellent. So things are working nicely. It is largely the same approach as the RC circuit when it comes down to the math, but obviously some of the concept that goes into the t equals 0 and t equals infinity behavior is now new and sort of asking for a different understanding of the circuit elements. So take some time, get some good practice with these LR circuits, and in our next video, we're going to really go out on a bang. We're going to put everything together from a circuit perspective. We've done RL, we've done RC, we've done R on its own, we've done L on its own, we've done C on its own. We're ready to put all three of them together for one of the most important circuits in this entire class. We see that we get some really important behavior from this circuit from an engineering perspective. It's a complicated circuit, so we're going to try to handle it mostly conceptually, but it really is a nice capstone for this course. I will see you in that video.